Greetings, mathletes, and welcome back. We're going to be taking a look at limits again today. This time we're going to take a look at it graphically. We're going to take a look at some of the rules of limits, what you're allowed to and what you're not allowed to compute, and then take a more serious look at the algebraic side of this. So without any further trouble, let's go ahead and get started here. And so I have this function defined. This is our function. We'll call it f of x. And I kind of zoomed in on this so you can see it a little bit better. So I want to point out some of the key points here. So first of all, note that like right here, that point is a closed point. That's a solid dot. But up here, that one is an open dot. And so I've discerned them, the closed and open dots, by red and white dots. So like here, there's no value here, but the function value is actually up here. Over here, there's a hole in the graph, right? There's just a hole there, and then I have a value floating up here all by itself. Okay, so just want you to take note of that because I'm going to zoom out on this thing so that we have a little bit of room to play around. And scoot that over a little bit. But that's our function. That's what we're going to be dealing with today. Okay, so if we're looking at this and we're talking about taking limits at different points, and now keep in mind these values that I'm choosing as far as what x is going to, I'm choosing them, I'm choosing them with a purpose to illustrate a point, but there's nothing particularly special about these values. You can use any values for these things, or you could be given any value. So let's start off by looking at the limit of f of x as x approaches 3. Okay, so this is what this means graphically. So first off, I want to find the point 3, right? Here's x equals 3, right? That's the x value. What I want to do is I want to be able to follow this function from both sides to this x value of 3. So as the x values close in on 3, and keep in mind, you want it in your mind, it needs to close in on the same number from both sides. What does the function do as the x value gets closer to 3? Well, you can look at it. Where is it heading? And it's heading to the same place from both sides, isn't it? Right? It's settling on a function value of 2. And so as x approaches 3, f of x approaches 2. And so the limit of f of x as x approaches 3 is equal to 2. Notice that happens to be exactly what f of 3 is. Note, f of 3 is equal to 2. What that means is that if we don't have, if this is a continuous function, we don't have any breaks in it or anything, all we have to do to evaluate the limit is plug in the number. Now, that's not significant now that we have a graph, but it will be when we're doing the algebra, because it's a lot easier just to plug something into a function than to manipulate everything and try to be creative about it. So a lot of these cases are going to be really straightforward. Now, oops. That's not how I wanted to do that. Oh, well. I'll just leave it here. We're good. All right. Let's see here. Now, I want to get rid of some of these here so they're not in the way. Yikes. There. Okay. Now, so this limit exists. We got a value of 2. Now, what if I wanted to look at the limit of f of x, and let's pick something else. Let's pick, let's see, that's at -7. So let's look at if x is approaching -7. Now, we have a big old jump in here, don't we? Right? If I look at this straight down on this x value, these two sides, this one, if I approach -7 from the left, right? I'm approaching a value of 3. If I approach it from the right, though, on this side, I get a value of 1. If you're getting two different values from two different sides, the limit does not exist. And that's a pretty common thing to write, DNE, for does not exist. Later on, there'll be other types of designations, because when a limit doesn't exist, sometimes there's different things you can do with them. But for right now, we're just going to identify them as not existing. Okay, so those are your first two examples. Now, I want to clean this up a little bit so we can take a look, but I want to point out that if there's no break in the function, then the limit is just whatever the function value is. If there is a break in the function, and each side goes to two different places, then the limit doesn't exist, because to exist, it has to go to the same place from both sides. Okay, so let me clean this here. Now, the one type that we're going to see that I find this the most interesting case, and that's the case here at 1, right? When I have, oops, switch over to brushes again, right? The type of discontinuity we have here, because that's a hole in the graph. Now, this type of discontinuity, let me go ahead and write the limit first, because we're going to be looking at the limit of f of x as x approaches 1. Note, and this is, I think really this is where you get the intuitive idea of a limit. This limit does exist even though there's a hole here, because if I head from both sides here, it's approaching the same value. In fact, that value is 1. It's not the function value. The function value is up here at 3, right? So f of 1 is equal to 3. But the limit of f of x as x approaches 1, well, we can see where that's heading from both sides. It's heading to 1, right? So the value of the limit is what the value of the hole is, I suppose. It's what the function value would be with the hole filled in. So this is the power of limits, is that when you have something like this is a way of being able to manipulate it and find a value when you actually don't have one there. In a lot of ways, calculus is kind of like magic. We create a lot of things that don't exist somehow. It's a real fascinating thing. But this type of discontinuity, when you have a hole in the graph, so the function is not continuous, but the limit still exists, is called a removable discontinuity. Right? And if you have a removable discontinuity, the limit exists, but the function value may or may not, right? And the function value is not the same as the limit. And that's kind of interesting, right? Because 1 is not equal to f of 1, right? F of 1 is equal to 3. But the limit as x approaches 1 is 1. So I know that I remember when I first went through this, I kind of felt like this was a little slippery. It almost seemed too obvious, where I felt like there really should be more. Well, I'll tell you this much. The graph is just for illustrating the concept. The more comes in when we start dealing with the actual algebra of all this, and that's where we're going next. So we've gone through the different types of discontinuities. Now let's look at the algebra. So let me go ahead and clear this off. Okay. I keep forgetting to turn that pen back on. Okay. The rules. Right? Now I'm going to explain what we're going to do with these rules. Many of these rules, you don't tend to use too many of them in combination, not explicitly. What you end up doing is using the consequences of all these rules to compute things. So let's go ahead and start with these. And some of these you will use quite often, just in a single form. But in any case, so we're going to start by saying that f of x and g of x are functions. Okay. Now, if I have the limit as x approaches c, and c is just some number, of f of x plus g of x, I can split them. I can look at this as the limit as x approaches c of f of x, and actually this is true for minus as well, plus or minus the limit as x approaches c of g of x. Right? Pretty straightforward. If you have two different functions being added together, you can take their limits separately. All right. Also, constants, if I have the limit as x approaches c of some constant k times f of x, I can pull that constant out and multiply it by the limit as x approaches c of f of x by itself. Right? So you can factor things through limits. Right? You can pull a number out. If there's a common factor that doesn't have a variable, like it's just a number, you can just pull it straight through the limit. And then the other two are also tied together like addition and subtraction. You have the same thing for multiplication and division, right? The limit of f of x times g of x as x approaches c is equal to the limit as x approaches c of f of x and the limit as x approaches c of g of x, right? So if you have a product, you can take the limits of each factor in that product separately, right? It's kind of nice. And then the last one is for division, and it actually works for division too. The limit as x approaches c of f of x divided by g of x is the limit, oh, this is going to get messy, as x approaches c of f of x divided by the limit as x approaches c of g of x, right? And that's provided that the limit as x approaches c of g of x is not equal to 0. If it's equal to 0, we have a problem, right? And we can either fix the problem or we can't fix the problem. Now, there's a sheet that I attached in the module that has all these rules on it. So you are free to continue to, you're free to use that. That's a reference sheet for you guys. Okay. Now, let me go ahead and get rid of some of this because there's two more I want to talk about. These are all the linear properties. I'll just do the rest this way. And there's some properties that go along with exponents also. And it turns out that the limit as x approaches c of f of x raised to some power is equal to the limit as x approaches c of f of x. Right? You can take the limit and then raise it to that power. So you can do the inside of an exponential expression. Also, the same holds true for roots. Right? The limit of the nth root of f of x as x approaches c is the nth root of the limit as x approaches c of f of x. Right? So that means that when you're taking the limit of a root, you can take the limit of the inside first and then just take the root. Now, all of those rules that we were looking at end up culminating in this nice little summary. So if p of x and q of x are polynomials, and we will be dealing with a lot of polynomials, then the limit as x approaches c of p of x is equal to p of c. Right? So if you're evaluating a polynomial, or if you're evaluating the limit of a polynomial, all you have to do is plug in the limit, right? So whatever c is, you just plug it into the polynomial and that's the value. And it's because polynomials have no holes, right? There's no breaks in a polynomial. They're continuous. So taking the limit of a polynomial at a point is the same as evaluating the polynomial at that point. So those are really nice. If you're evaluating the limit of a polynomial, those are the easiest ones we're going to be doing. Where we start looking at kind of tricky stuff is when we're looking at the limit as x approaches c of p of x over q of x. As long as q of c isn't 0, then this is just p of c over q of c. But again, q of c can't be 0. If q of c is 0, we have to do something, right? Or possibly the limit just simply doesn't exist. We were talking about those removable discontinuities before. If you have a removable discontinuity or a hole in the graph, I'll just call it that. This is a removable discontinuity. What happens when you take the limit as x approaches c? Oops. Right? What you end up when you plug in p of c and q of c, you get a 0 over 0. Okay, so when you get that 0 over 0, that's a removable discontinuity. At least, well, we'll look at examples. We'll see what this looks like. Most of the time, at least the ones in this chapter, if you get a 0 over 0, there's a way of getting around it. Okay, and that's where the creativity comes in. So this case is the one we're going to end up focusing on mostly as far as our examples go. So I've given you all these different rules. Let's just see how they play out now. Okay, so let me go ahead and clear that, and we'll get our next example up here. Okay, so here's a couple of examples. All right, so this is how we take a look at these. So first of all, the first thing I notice is this is a polynomial. And as a matter of fact, if you really wanted to, you could picture this polynomial. This is a parabola because it's x squared and it's moved up by 3 units. There's no holes in parabolas, which means we're not going to have any discontinuities, which means the limit exists everywhere, which means if I want to compute this limit, I just plug the 2 in for x. So this now becomes 2 squared plus 3, which is 7, right? No problems, no muss, no fuss. That's true for every single polynomial. If you're taking the limit of a polynomial, plug in the limit. Okay, now over here we have a rational expression. We have a polynomial divided by a polynomial. So I do run the potential of having something that having a limit that doesn't exist here. But we want to take a look. So we can tell if this exists just by plugging this in, or I can tell if I need to do anything just by plugging in the 3 and making sure the denominator doesn't come out to 0. Right? Because it's division by 0 that's going to cause a problem. But if I plug in a 3, right, if I just evaluate this at 3, it comes out to a nice number. So this denominator ends up being 8, and this is 9 minus 9, so that's 0. So that means the limit is 0. There's no problem with the numerator being a 0. It's the denominator being a 0. Okay, so this limit exists. And that's because there's no holes where I was asking to evaluate, right? At 3, there's no holes. There's a hole when x is negative 5. And actually, it's not even a hole. It's worse than that. You can't remove it. Right, so this answer is 0. So as long as the denominator is not 0, evaluating the whole thing is just fine. Okay, so those are the nice ones. Now let's focus on the ones that aren't so nice. So let's clear that off. So, yeah, we'll start over here. So let's say I have the limit. Try it again. Let's say I have the limit of u to the 4th minus 1 over u to the 3rd minus 1. And this is as u approaches 1. Okay, so first off, we can see there's problems, but we're in luck because if I plug 1 in here, what I end up with is 1 minus 1 over 1 minus 1, which is a 0 over 0. So that means we stand a chance of removing this discontinuity. What we're doing, if there's a hole in the graph, by factoring things out and canceling a common factor, that common factor is typically the factor that made it 0. And so you can eliminate that factor, and basically it's plugging the hole in the graph so you can see where it goes. So let's see what we can do. We're going to have to factor this out. Now, just because we haven't factored in a while, I don't know how long it's been since you factored. I'm going to go ahead and walk through this process with each one of these. So let's see here. That's the difference of squares. So that's u squared plus 1 times u squared minus 1. U squared minus 1 is still the difference of squares. So this one stays the same, and now this is u plus 1 times u minus 1. Okay, so that's my numerator now. So now I'm looking at this. Right, and then the denominator we need to factor now. So this is the difference of cubes, and there's a formula for that. So it starts out with u minus 1, that's a minus b, times a squared plus ab plus b squared. Okay, and so I'll write that one in. And we can see right here, this factor is the one that's causing the zeros, right? The u minus 1. If I plug in 1, those are the factors that turn into zeros. That's what's killing everybody. So we've just removed it. We've plugged the hole. There shouldn't be a hole now. So what we can do is just plug 1 into each one of these terms and see what I get. And so that's what I'm going to do. If I plug a 1 into u squared plus 1, well, 1 squared is 1 plus 1 is 2. So that's now a 2. That becomes a 2 also. And then if I plug this in here, that's a 3. So if I evaluate this whole thing, I end up with 4/3. But what's really happening here is there is a hole in the graph, and that function value is 4/3, and the x value here is 1, right? So what we're doing is we're figuring out where this function goes without the hole, basically. And that's what the factoring does. So this is going to be the trick. You need to know how to factor, for one. That's going to be important. In fact, I think I'll go ahead and add to the module an extra video in case you want to watch it on how to factor. So let's go ahead and take a look at the next one. Okay, so this time we're looking at the limit as x approaches -1 of, let's see, we got 3 subtracted from the square root of x squared plus 8 over x plus 1. Now, I think we can see right off the bat, if I plug in -1 into that denominator, I'm going to get a 0. So the only question is whether we get a 0 for the numerator as well, because if we do, that means there's something we can do. We may be able to find this limit. So let's see what the numerator comes out to. And if we plug in -1 here, right, that becomes a +1. So now we're taking the square root of 9, which is 3 minus 3. That also gives me a 0. So that's the indeterminate form. When you have a 0 over 0, that's not technically undefined. That is indeterminate. It may turn out that the whole thing ends up being undefined, but we can't determine yet because 0 over 0 isn't a proper value. So we need to do something with this. And the trick, typically, when you're looking at these, is to manipulate them around so that you so that you move. Try that again. You want to manipulate these usually through the conjugate, and you're hoping to eliminate something. You're hoping to eliminate the discontinuity. Wow, I can't talk this morning. Okay, so let's see what we can do. Typically, when you see some kind of radical expression, what you're going to end up doing is multiplying by the conjugate, which is the exact same term, but you change the sign between the root, either between two roots or a root and a number. So that means that we are going to multiply by the square root of x squared plus 8 plus 3 over x plus 1 times the square root of x squared plus 8 minus 3. Now, one of the things I want to point out is a lot of the time when you multiply by these conjugates, the only one you're actually going to multiply out are the ones that are conjugates. So one of the things that's nice about conjugates is they're really following this pattern, right? The difference of squares. So really all I have to do is square the first term and subtract the square of the second term when I'm computing these things. So squaring the first term gives me x squared plus 8. Squaring the second term gives me minus 9. Well, it's always minus between, right, because of that. And then I'm just going to leave x plus 1 and square root of x squared plus 8. Oops, that should be plus 3. Plus 3. It factored in the denominator. I can see from here that this is going to be x squared minus 1, and x squared minus 1 factors as x plus 1 times x minus 1, right? Which means that I can cancel this out, and let's write down what we have left now. So this is the same thing as the limit as x approaches negative 1 of, well, that's the only thing left in the numerator, x minus 1 over the square root of x squared plus 8 plus 3. Now, I already know that the denominator is not going to be 0 because any square root spits out positive numbers, and I'm adding a positive number to it. So that's going to be another positive number. We're going to be okay here. So if I go ahead and compute this, if I plug in negative 1 for x in the numerator, I get negative 2. And if I plug in negative 1 in the denominator, that makes that, I'm just going to do a little scratch here right underneath it, right? That makes it 1 plus 8, which is the square root of 9. So that ends up being 3 plus 3, which is 6. So my final answer is negative 1/3. And you can see that's a lot of work. You got to play around with it. You got to do some multiplication. You got to be a little bit creative. I will tell you, almost always when you're dealing with roots, you're going to be dealing with a conjugate as far as simplifying things and eliminating the removable discontinuity. Or I should say, well, eliminating the removable discontinuity means that we're putting it back, really is what we're doing. We're plugging the hole so we can see what's there. Okay, so that's dealing with roots. All right, so let's go ahead and clear this out. Now, one more example to do here, one more necessary example, and I think I'm going to do one more just to give you a little foreshadowing here. Okay, so here's our last official example. This one may or may not jump out at you, but you know what, it might be a good idea just to see what you can do. This one's a little different than the rest of them. So why don't you pause here and see what you can come up with on your own, and then go ahead, once you either hit a wall or solve it, go ahead and push play and see if we match up, or just to see the solution. Let's see here. Yeah, so let's go ahead and get started here. I'm assuming you've already paused it. Now, you have to remember what it means when you have a negative exponent, right? Negative exponents mean division, which means that this is now the same as the limit as x approaches 1 of 1 over x minus 1 over x minus 1. Okay, so I'm just going to pull this expression out over here, and we're going to play with it. Because you notice when I plug in 1 here, the denominator is 0, and I get 1 minus 1. So the numerator is also 0. So this discontinuity should be removable. So let's see if it is. Let's see here. We have 1 over x minus 1 over x minus 1. Now, one of the tricks, since you are allowed to multiply the numerator and denominator of any fraction by the same number, is to multiply the numerator and denominator by the common denominator among your fractions. And since I only have 1, the common denominator is x. So I'm going to multiply top and bottom by x, and we'll see what we get. Okay, so here the x's will cancel to give me a 1, and then x times 1 is x. So this is now 1 minus x, and I'm not going to multiply out the bottom. I'm going to leave it factored because, you know, that's what we need. Now, nothing matches exactly, but you notice, right, I have a positive x here and a negative x here. I have a positive 1 here and a negative 1 here. So that means if we switch all the signs, it'll match up and cancel out. So I'm going to factor out a negative and make this x minus 1. And so now this is that. So I can cancel this, which gives me negative 1 over x. So now this has been changed to the limit as x approaches 1 of negative 1 over x. And that's one we can just plug in. There's no discontinuities for this particular function at 1. The only discontinuity is when x is equal to 0 here. So if I plug in 1, I get negative 1 for the limit. Right? So you have to be a little bit creative. We had a couple of things there. I had to clear those denominators, and then I had to reverse the order of a subtraction by factoring out the negative. Right? So those were the two things that that we really had to do there. And once we did that, we got it down to something that we could evaluate at 1. Now, here's my suggestion to you guys. This is kind of an aside. Here we go. When you're going through these, especially if you struggle with these problems, what a really good thing to do as far as studying goes is what's called the white paper test. And I don't know how official that name is. It's something one of my professors told me, and it really did change the way I did school. What you do is after you've gone through the lecture, you write down one of the problems, and you should do it with all the problems from the lecture. Write it down at the top of a blank white sheet of paper, put all of your materials away, and see if you can work out the problem from beginning to end. If you can't, go back and watch the video again. Go back through your notes. Figure out why you're not able to do it on your own. Once you're able to do it on your own and get from the beginning to the end without having to look at any other materials, that means you understand that particular problem, right? And probably the method that goes along with it. And so now you can see if you can apply it to another problem. It's a way of testing yourself to see if you actually understand it before it comes to crunch time, where you have to understand it right now. But I spent a lot of time as a student just doing the white paper test. And I didn't get exposed to it until we were doing proofs and things like that. But it really does apply. It applies to pretty much everything. Okay. That being said, that's probably the end of what you want to see, but I have a little bonus for you. I want to look at some trig functions just so you have an idea of what it looks like with trig, because we're coming up on that soon. But it's the same concept. So let's take a look. Let me go ahead and delete that, and we will look at the limit as theta approaches 0 of 5 times sine squared theta over 1 minus cosine squared theta. Okay, now looking at this right off the bat, sine of 0 is 0, so that makes that numerator 0. Cosine of 0 is 1, right? So now this is 1 minus 1, which is 0. So I have a 0 over 0 here, right? And that's a bit of a problem. So I need to be able to handle this somehow. Well, this is where identities come in. This is why it's important to know your identities. This denominator, if I look at the Pythagorean identity, right, and I just subtract cosine squared over, I find that sine squared is equal to 1 minus cosine squared theta. Right, which means we can substitute. So this is now the limit as theta approaches 0 of 5 sine squared theta over sine squared theta, right? And that cancels, right? So those cancel out. Now, really, and this is the part that's kind of weird. If I have the limit as theta approaches 0 and all the variables eliminated of 5, right? Think about what that is. It's a constant function at 5, right? It's horizontal and it goes straight across at 5, which means the limit has to just be 5. It's going to be 5 everywhere, right? So it's one of those things where you're going to need to know your identities and you're going to have to get kind of creative with them. We're not quite there yet, but I want to fold a little bit of this in there just so you get an idea of what's coming. It's really some good stuff. Okay. Now, okay, so that concludes the lecture. That's as far as I wanted to go today. Keep in mind that this is actually what we were doing with the difference quotient in the last lecture as well. So until next time, keep your pencils and your wits sharp.